Hello, everyone. My name is Elisa Baum, and I am Percona's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct a bit of house cleaning. First, could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? Okay, great. Thank you very much, everyone. See lots of hands. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the GoToWebinar control panel. At the end of this webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog post on Percona's MySQL performance blog. In addition, I'll make sure everybody here gets a recording of the webinar within 48 hours. I would like to thank you for attending today's webinar, Optimizing MySQL Performance, Choosing the Right Tool for the Right Job. Today it's going to be presented by Marcus Albee. He is a support engineer at Percona. And in addition, Matt Griffin, who is Percona's Director of Product Management, will be joining Marcus for the question and answer part of the show. And with that said, I'd like to turn the floor over to Marcus. Go ahead, Marcus.
Hello everyone, my name is Marcus Albee and I'm here to talk about optimizing MySQL performance, choosing the right tool for the job. For those of you who aren't familiar with Percona yet, we do MySQL consulting, support, remote DBA, among other things. And in our consulting and support practices, we are often asked how to diagnose issues unrelated to MySQL, like Nginx, Hibernate, Apache, Redis, general Linux tuning. And for all this work, we use a certain toolset that we're going to be presenting here. I usually tend to split the word between developers and sysadmins. Well, you can get much more divisions, but I usually tend to divide in those two groups. And developers usually see the world through their applications. So when they start tracking performance issues, they start adding instrumentation to the code or using code profilers to see which function is spending more time. And then they can go down the stack and see what function is doing it and why it's so slow. Sysadmins and database administrators, on the other hand, will usually investigate performance from the bottom down. So they go from the perspective of the system they administer, and they will look at resource utilization to find where the bottleneck and where the bottleneck lies, and from there they will go up the stack and see what's actually hammering the specific resource they saw the suffering. As a consultant, I generally have to follow the path of the system administrator because it's cost prohibitive for me to try and instrument unfamiliar code base or the whole MySQL code base. You can imagine that's about 1.5 million lines or something like that. So it's actually impossible for me to add instrumentation code there. So the tools we will see here are tools that allow us to profile code without adding any profiling code ourselves. However, the best approach is to have both paths available. So if you know your code, add your own instrumentation code, and also use these tools to improve your debugging code from the developer side if you're a developer. So here is our agenda for today, and I'll try to keep the presentation to around 40 minutes and leave time at the end for the questions. But it's a long presentation, and we might not fit all the content. Okay, so if you have doubts, you can later send me an email, and we will send a follow-up blog post, as Alicia mentioned. So we will quickly start with the what, why, and the resources that compose a server. Then we will go through the tools that are available on most Linux distributions, and then we will go through some Percona tools if time's allowed. So what are we talking about? The purpose of this talk is to introduce the primary tools used for obtaining and collecting metrics and status information about system components, and which is the corpus for investigating performance issues affecting MySQL or any other service. The talk, again, is focused on Linux environments and will cover the most commonly available tools. And it is certainly not meant to be exhaustive, so these are our favorite or the most ubiquitous tools we know.
Marcus, sorry, real quick.
Yes.
Can you change the system preferences to increase the volume of your mic?
Yes, just 1 second.
Thank you.
Yeah. System preferences. Let's go where it is. Sound. Output volume. Is that better? Hello, Matt.
I think it's a little better.
Okay. Can you hear me there? Is that better?
Yeah, perfect.
Okay.
A little better. Thank you.
Thank you. So, why we care about system performance? There are 4 primary reasons that we want to learn about system performance. The 4th of these reasons we won't talk about today is simple intellectual curiosity. But there are 3 good reasons we all want to become better with performance optimization. We all know that quick and consistent response times are fundamental to most aspects of online businesses, as well as offline ones. Unfortunately, hardware seems to shrink with respect to our growing datasets. Applications have bugs and bad queries, and finding and fixing the performance bottlenecks in the system is a difficult task that sysadmins and DBAs must do day to day. So having a method and knowing how to use the tools available can prevent issues or significantly reduce the amount of time between problems manifesting and fixes being deployed, which of course equals money, because you're saving customers and you're getting more sales than on time that could have been wasted on an outage. It also helps to make the most out of your hardware, extending the purchase lifetime and alleviating your IT budget. And furthermore, throwing hardware that problem is not always possible or is not always the best solution. So it's a way to solve production issues. So finally, the knowledge of your workload and the resource consumption should help you to plan for growth. It should be noted that capacity planning is not trivial, and we won't be talking about this today. It's a whole topic on its own, and there are several books by Neil Gaiman that are awesome, but are really depth into calculus. So, but without the basic data the OS provides about your workload and the performance, you wouldn't be able to actually predict any growth. So it's important for that too. So next, we'll talk about the resources. All systems are composed of a few basic resources we all know and love. And these are the CPUs, the RAM, the storage, and network components, as well as other virtual resources like semaphores, mutexes, or buffers, which of course those consume hardware resources on their own. So sometimes we will see these are the bottleneck, and we will have to find out if it's a problem with the algorithms the mutex or a semaphore is using, or if it's a problem that the hardware resources they use are being depleted. But it's important to understand these are also resources. The hardware of our system and the algorithms we use do have limits, do have physical limits, because light can travel only so fast in a nanosecond, and that's about like 6 or 8 inches, I can't remember, but there's a physical limit that light can travel, and that will be the physical limit for computers too. So we must learn and understand our hardware and system limits before deploying into production. So we need to set up and run proper benchmarks so we know their general capabilities. And benchmarking is also a whole other topic that we won't be going through today. but you have to really run benchmarks of your current production systems and of the QA systems you are planning to deploy later, because that is what will give you foundation for later analysis. So, because when a performance problem arises, it must be one of the resources that must be saturated, and thus the investigation starts with them. And so I personally first look at the hardware status a bit before going into MySQL in order to have a better idea of what to look inside MySQL. And to check also basic stuff, like we have a pre-flight list, like it's swapping, there's a huge number of threads running, or it has a disk full, or is the battery for the RAID controller in good shape. So after we look at the hardware, we will go after the problematic process we see consuming the resources, which could be often something other than MySQL. So next, onto the tools. Most of you should recognize these tools as part of your standard toolkit. They are included in most Linux distributions, and they represent the bare minimum tools that you should have installed for diagnosing performance issues. Well, we have top, which is a general monitor snapshot. vmstat, which is good to get a general monitor with a time series, so it will allow us to see an evolution more clearly. iostat will give us all the workload and performance metrics for IO storage. GDB, it allows us to grab back traces and to do other black magic. oprofile is a system-wide profiler that allows us to see which functions are being called the most often. strace allows us to call the system-level calls, and this is very useful. It has unlimited uses. Netstat and ETH tool are tools that come handy when we have networking issues. And TCP dump allow us to do all sorts of magic also at the networking level. So this second slide has the Percona tools that are part of all the Percona toolkits, and this won't be included in most Linux systems, but nonetheless our consulting team uses this very often and has driven the toolkit to a status of, like, it's a really good toolkit, well developed, well tested, and we feel that the tools in the previous slide were lacking the strength this has for DBAs. So these are really the DBA tools. And if we don't get to cover this today, we will soon have a webinar about them. So stay tuned, and really, if you're into DBA and you haven't got to know our toolkit, do pay attention, because it's an awesome toolkit. So, sorry. You should read the man pages for each of these tools, because the command line options tend to differ among distributions and versions. And for those of you which are not on Linux, so those BSD, Solaris guys, you will find very similar set of tools available. For you Windows users, I don't know what to say, other than this talk probably isn't for you unless you're using SSH to your own servers. So you probably know the tools from your servers and not from your own desktop. Anyway, there are 3 occasions when you should be using the tools we will be presenting. When you originally benchmark the system, during normal operations, when no issues are happening, and when a problem is happening. And it's very important, as we mentioned it earlier, to go through all these contexts, because your benchmarks should show you the general capabilities of the hardware. This is the benchmark. And this will be your reference point for when forecasting the need for additional, bigger, faster, better hardware. And you must also have a baseline of the output of these diagnostics when the system is operating normally. And it is against these measurements that you will compare measurements during an outage so that you can see what is going wrong. For example, if you only run these tools during an issue, you may see that CPU is at 90% usage, and you might start chasing a CPU problem. And if you will only find out that the system normally operates with that amount of load on the CPU, and that the problem was actually a saturated network or a problematic router elsewhere. So we need to know what this normal baseline system looks like before we dive into investigating performance issues. So on to the tools. Tool number 1, top. So we've chosen top as the number 1 tool because it has been included in standard Unix distributions since 1984. It's also probably one of the most underrated tools. And you just have to read the man pages to realize how powerful it can be. It's great for quick view and to watch how load evolves, because it has a 1, 5, and 15 minutes moving averages, which will tell if the trend is going up or down. And it allows us to quickly browse through processes and find which ones are consuming which resources. It works based on a refresh rate. So if something runs faster than the refresh rate, you'll never see it on the process list, but instead you will see the load increase. It might have caused it. In other words, you won't see 100% of the running processes sometimes, but the load indicators that top provide do take 100% of the system into account. So here we have a sample top screenshot many of you are familiar with. In the first line is a quick status with date, uptime, users, and load average, and the 1, 5, and 15 minutes average. So you can see if the load is increasing on the system. So if the 1 minute, I'll go into this later. Sorry, let me go very quickly through the whole screenshot. So the load average numbers in Linux refer to the sum of the number of processes waiting the run queue plus the number currently executing. The number is absolute and not relative, so it is unbound, unlike actual CPU utilization. This means that even if I have only 8 CPUs on my box, I could see load average of 20 here, and that will mean that I have at least 12 waiting processes. We are often asked a simple question, which is, at what load average should Nagios start alerting? And the easy and stock answer is when the load average equals or exceeds the number of CPUs in your system. So if you have 16 cores, you will trigger the alert when the load average hits 16. But we actually disagree with that answer, and it's good as far as it goes if you have no knowledge of the system. But the correct answer is that you should alert before whatever load average will cause you to miss your SLA. You will know what that number is based on the benchmarks and production observations we recommended to go under earlier. So those are very important, as you can see. And continue with the top screenshot. The second line is the process summary, total processes, running, sleeping, stopped, and zombies. And that's a great interview question. What's the difference between an orphaned process and a zombie? I will leave that one for the end of the presentation, and see if any of you guys can type that one into the questions, and you can get into a virtual raffle for that one. So the third line has the CPU load with user time, system time, nice time, idle CPU time, IO wait, hardware and software interrupts, and the little known steal time. We will go over this in a few moments also. The fourth line shows memory information with the total used, free, operating system, and file system buffers. And the last summary line is swap info, displaying the total. Oh, the question is, Alisa is asking me to repeat the question. What is the difference between orphaned processes and zombie processes? So we can go over that when we get to the questions. So the fourth line, the last summary line is the swap info, displaying total swap available, how much is used, how much is free, and how much of that swap has been cached. Then it lists all of the processes ordered by whatever you choose to order them by. In this case, they are ordered by CPU, but I usually also tend to sort by memory or by running time. You could also see in which state each thread on the process is, so you could sort on that too. It's actually top is actually a very complete tool. And well, one of the most interesting lines is the third line, telling us about CPU. And the user is the CPU time that is spent running the actual code the user provided. Could be your MySQL process, your Apache process, your Nginx, your PHP scripts. And so this is how much your software has been running, and it doesn't take into account netstat processes. SY is system CPU time, and is how much time we spent on system calls, which are the calls between the user, software, and the kernel. The NI is the nice CPU time, which is how much time we spent running user processes that have been niced. And WA is IO wait, which is the amount of time the CPU has been waiting for the IO to complete. Anytime folks deal with persistent data, they tend to focus on this metric because disks are traditionally the slowest component in a computer system. And HI is the amount of CPU has been servicing hardware interrupts, and SI it's how much it services software interrupts. And the little known steal time is the amount of CPU stolen from a virtual machine by the hypervisor for other tasks like running another virtual machine on the same physical host, or moving the virtual machine to a different node. Whatever you are doing, whatever the hypervisor is doing, it can elect to steal time that should have been assigned to one of your virtual machines. You will see that reflected on the ST on top. An interesting note is that Amazon exposes this information. So if you're using EC2 instances, you should make sure to keep an eye on the steal time to make sure you're getting your money worth from your instances. And if you see it's going above, say, 1, 2, 3%, something like that, you should actually consider simply stopping that instance and getting a new one. So next tool is vmstat. When I engage with a performance issue, one of the first tools I use is vmstat because it quickly provides compact information about the various system resources and related performance problems we can see with them. It reports statistics about the kernel threads in the run and wait queues, memory usage, patient activity, disk utilization, interrupts, system calls, CPU activity, context switches. So basically, this is a good system health dashboard. We used to know where we should head to with our next investigation steps. It is rare that you can fully diagnose an issue using just vmstat, but it's the best place to start probably. And here's a quick sample, and again you can see here's the column by column breakdown actually. So under procs, there is the R column, which is the average number of runnable kernel threads over the sampling interval, meaning threads that are ready but waiting to run, and those threads already running. B, under procs, also is the average number of kernel threads placed in the VM wait queue, waiting on some resource or waiting on I/O. Under memory, we see swapped, which is the amount of virtual memory being used. We see free, which is the amount of idle memory. We see buffers, which is the amount of memory used as a file system buffer. And cache, which is the amount of memory used for swap cache. Although it is not shown here, you can also get to display the amount of inactive versus active memory with the A option, usually. Check your man page, but usually it's the -A option. Under swap, we have swap in and swap out. Swap in is the amount of memory swapped in from the disk, and this is the bad thing. This is seriously very bad. A page in or swap in operation occurs when the server is experiencing a severe shortage of RAM. And while all virtual memory servers will tend to page out to the swap disk, a page in operation is showing us that the server has exceeded the available memory. Any non-zero value for SI indicates excessive activity as the memory contents are reading from the swap disk. Oops. And just to clarify, it's important that you ignore the first line of metrics. It's really the differentials, the next lines with the differentials that you care about, not the past performance. The first line is only the average past performance. So you should ignore those. Next, swap out is the amount of memory swapped to disk. This might be unnecessary, so you can go ahead and check your VM swappiness with syscontrol. And this should generally be 0, but if your swappiness is at the default of 60, it's possible that you will see the system slowly tends to page out things. But the problematic one is page in. So SI is the bad one, SO is not so good, but keep an eye on it, but it's not terrible. Next column is BI, which bytes in, which is telling us how many bytes went read from disk, and bytes out, BO, which is telling out how much disk writes we are doing. This can be a very interesting indicator to see if your INDB buffer pool is sized appropriately, because if you're getting a lot of disk reads, it means that the hot data set does not fit into memory, and you can potentially avoid a lot of disk reads by increasing the buffer pool size, which may require additional RAM, but RAM is faster, and in the end it could be less expensive than buying a whole new I/O subsystem. Then under system, we see interrupts per second under the IN column, context and context switches per second. Just to explain what a context switch is, when a CPU is running a thread and this thread has depleted the time the kernel scheduler has allocated for it to run, then the CPU needs to store this thread context and load the context for the next thread that it will execute. So this is the context switch. It's switching the context for execution of a thread. For say a 16 core server, a 60,000 is already quite a bit, and is hinting us about mutex contention or too many running threads. That's a generalization, and you should track how many context switches are normal for you and at what point your SLA will start suffering. So that's important part, but 50, 60K is already quite a bit. And then CPU reported activity is a percentage we already see before. System, idle, weight average, and still we saw this on top. So I won't go over it again. So next is iostat. and as you can guess, it will give us information about I/O performance. The tool is quite ubiquitous and makes it a favorite, but I personally prefer one from Percona Toolkit called PT Disk Stats. And if you really need to get good disk stats, go with the Percona Toolkit one. It's free and it's easy to set up and use, so try that one too. So if top or vmstat gives you any indication that the problem might be in the I/O subsystem, remember the WA column. So then I would go to iostat or PT disk stats. We're only going to show the extended device report here in this screenshot, which is the one you should always use anyway. So that's -dx options for iostat. So quoting Brendan Gregg, the iostat is split in two parts, work and performance. And the following columns are the ones showing us the work that has been done by the I/O subsystem. Our RQM and RWQM is the number of transfers per second that were issued to the device. And a transfer is an I/O request to the device. In other words, this is how many times your application sent a request to the I/O subsystem. IOPS, on the other hand, is how many your hardware can deliver without increasing response times. And this is multiple logical requests can be combined into a single I/O request to the device. So our RQM and our WQM are how many were issued, and RS and W/S are the number of already merged request operations completed to the device. The sum of these two is the IOPS of your storage subsystem has delivered. So this is how many you have done, the hardware has done. The first two columns is how many your software requested. The second column is how many the hardware actually did. The fifth and sixth columns, average RQ size is the average size in sectors of the requests that were issued to the device. A sector is 512 bytes, remember. And the average QU size is the average queue length of the requests that were issued to the device. If you see the average queue length increasing, we can tell there are either too many requests incoming or that hardware response time is too high and things tend to pile up. So if the queue length is building up, you might consider adding more drives to your RAID in order to achieve a greater degree of parallelism for requests. And later, RSEC and I missed RSEC and WSEC, sorry. RSEC and WSEC are the data per second from the device. This is also expressed in blocks. So all those first six are telling us about the workload. This is how many requests my software sent, how many the I/O subsystem delivered, and how much data in bytes that represented. And the next 5 columns will tell us about the performance of the I/O subsystem. So I already explained average request size and average queue size. Later we have average weight, which is the same from top or vmstat, is how much CPU, how much is the average wait for a request to be completed. This is expressed in milliseconds, and this includes the time spent by the request in the queue and the time spent servicing them. And we like to call this the I/O latency. And when we see latency above 5-7 milliseconds, it should be a concern. Service time is always wrong, and it's going to be deprecated soon, so you can simply ignore it. It's supposedly what's the average time for a request to be serviced. And percentage utilization is also always wrong, in the sense that it's only telling us how much time the I/O subsystem was busy, but not actually if the I/O subsystem was saturated. It has been busy 100% of the last second, but it was not saturated. So the key metric is when we see 100% utilization, we need to look at A weight and see if the latency is increasing. If latency is not increasing, then the 100% utilization is not a problem. So on to the next tool, which is oprofile. When the performance issue is related to CPU, one of the things we suspect first is contention, mutex contention. When we don't see mutex contention, then it's quite likely that we can find a bug in the software, and for that we need to use a profiler. And oprofile is the tool for this. It allows us to easily pinpoint queries or processes spending too much CPU through function calls. So we will see the MySQL function calls itself. The oprofile is typically invoked by being attached to a specific process to gather metrics, and this means that we need to have a general idea where the problem lies. So in general, for DBAs, it will the database process. Oprofile runs transparently on the background, and data can be collected at any time, but it does have a performance impact, so be careful when running it because it will impact performance of the system. It uses the hardware performance counters provided by Intel and AMD. And the key idea here is that we don't need to add the instrumentation code to the server ourselves. So we can do this with any Linux package, Linux software that provides debugging symbols. So here we have the basic set of commands that will get you going to profile your favorite application. I won't read through this because there are a million tutorials online. But basically you need to prepare the environment for oprofile, then initialize it and start collecting the metrics. I'm sure the slides are going to be available after the talk, so no worries. You can simply go and download the slides and follow this exact command lines. I have used it in many system production systems, so they will work perfectly. Then after initializing the oprofiler, this should be done exactly before the problem starts, or if the problem is ongoing, simply we start it at any time. So after we have the profiler running, we let it run for some time to collect data, and we then produce a dump and report on the dump, and then stop the profiler to avoid further impact on the performance, and then simply clean up to avoid gathering too many files. It can grow, disk utilization of oprofile can also grow quite large, so be careful. So the interesting part about oprofile is of course the report, and it looks something like this. And as you can see, it shows how many times the function was seen. That's the samples column. The total percentage of CPU this function consumed. The binary or library name path, and the symbol name. So in the first line, we can see that my hash sort simple function from the MySQL binary has been called 23,000 times and occupied about 27% of our time. So conceivably, if we eliminate my hash sort simple, we will have increased the theoretical capacity of the box by 25%, and that's quite a bit. So with this information, you have basically 3 paths to go down. First, you can go to the source and figure out what is going on and develop a fix. That's what we do when we don't know. We ask our developers to do that. Second, you can consult a service like Percona that can tell you what that means. And if we don't know, we will ask the developers. And you can also, as a third option, go to Google and search for the function name, and that usually will also help you a lot. This oprofile, for example, is from a MySQL 5.5, and with a quick Google search for the function name, my hash sort simple, it revealed that 5.6 release note stated this was a known issue, and it was fixed in 5.6. So we reran these benchmarks in 5.6 and did the oprofile again, and my hash sort simple was gone from the top resource consumers. So actually, someone found the bug and fixed it before. So this can come quite handy when the CPU is being hammered and you can't pinpoint why is doing that. It's not waiting for I/O. It's not waiting on new fixes. So what is consuming so much time? The oprofile will help you learn. So on to the next tool. We won't get to a tool which is called perf, and perf is a modern replacement for oprofile. So it's worth to investigate that. Feel free also to ask about perf at the end of the talk. But let's move to the next slide because we're running out of time quickly. Our next tool is GDB, and for those who know GDB, they probably love it. For those who don't know it, be careful. GDB is the GNU debugger, and it allows you to do all sorts of magical stuff, including the one that interests us the most, which is obtaining full backtraces from all the MySQL threads. We will also see some neat tricks that I'll show you as part of this, but be careful with these kind of tricks we will show, and be careful when collecting backtraces, because GDB can crash the MySQL process. I have been using it for several years now and never had it crashes on my face, but I have at least one colleague that saw a crash on his face. So the chance is there, so be careful. So a backtrace is the chain of function calls performed to get to the current execution point of a thread. For example, the slave SQL thread of MySQL has this signature while it's idle. And so you need to read this from bottom to top. And first, we can see that the MySQL D process called the clone function from the libc library, then used the pthread start thread function. From start thread, it called handle slave SQL that was on slave CC on the MySQL package. Then exec relay log handle slave SQL called exec relay log event, which in turn call it next event, which in turn call it MySQL being log wait for update. So we can see the thread is currently waiting for an update and is doing a conditional wait being handled by the pthread library. So this is not very interesting, but we can see, we will see a more interesting one in a minute. These are the commands you can use to get backtraces with GDB. You can get a regular or full backtrace, and you can get a full tutorial or explanation online if you like. The raw output of this command is a bit hard to read, and it's quite extensive. So the idea is to collect these backtraces and aggregate them with the poor man's profiler, which produces a much nicer output like this. So Percona has its own packaging of the poor man profiler script. The poor man profiler was invented by Tomas Mitutsas from Facebook, and it's a great tool. What it does, it's aggregates the threads that had the same signature. So if we read this slide from the bottom, I can tell you there was a single thread that was running start thread, signal hand, sig wait. And there were 2 threads that were running do handle one connection, dispatch command, execute SQL com select, blah, blah. And then there were 10 threads that were doing a start thread, IO handler thread, OS, AIO Linux handler, OS, AIO Linux collect, etc. So I can tell how many threads were in a given state. And I can see the state of each thread in the server very quickly. This helps me evaluate interaction among threads sometimes. And we will see that whenever a thread with a certain signature shows up, others will stack in a certain part. So that helps us unveil problems and find bugs. So again, you can get the whole thing, the GDB backtraces and the Percona profile with PT, PMP. Otherwise, you can go to percona.org and grab the script and extract the profile from your own backtraces. So on to a bit more interesting things. Here are some dirty tricks that we can do. GDB allows you to attach to running code and poke around, like adding breakpoints or some error conditions and change a variable. And generally, anything that you can think you can do with your debuggers, GDB allows you to do with the running process on Linux. So, for example, here we have a trick Aurimas from our consulting team came up with to overcome the too many connections error. If you ever get a too many connections and you don't care about that server, you can go ahead and try this. Simply run all those lines in bold on a command line, and that will set the max connections to 5,000 on the running MySQL. You can see the full article on our blog. The link is there. Basically, again, this is only so you can shut down the server cleanly or to investigate why all the connections were depleted. It shouldn't be a common practice or something that you want to do on your production servers. It's a dangerous trick, but sometimes it's a good trick if there's nothing else we can do and we will have to kill the server anyway. This might be better than killing the server without trying first. Sorry. Here is another nice trick. If you ever get an annoying LSN is in the future on your error log from InnoDB, well, you can actually go ahead and follow Nikolai's advice and actually advance the LSN to the future to make it match and then get rid of the issue. This, again, is just an experiment. It's just to show you the power of GDB, and it shouldn't be done on a production system. It's more a showcase thing. That's something that you will use regularly, but if you ever need to come up with how to find where MySQL is crashing, or you want to track what MySQL is doing at an exact point, you can know. GDB is the tool to do that kind of things. Thomas has a great collection of GDB tricks, so make sure to check his site as well. The link is there. And let's move on to the next tool, which is one of the most interesting for me, which is strace. Strace is useful to chase high system CPU usage. When we see SY percentage, the system CPU usage is going high. Well, and it's also useful for other performance or erratic behavior problems. And like oprofile, it executes or attaches to a command until it exits. And it shows the system calls the command does, and the signals which are received by the process as a response to the system calls. By default, the name of each system call, its argument, and its return value are printed on a standard error to the specified output. But strace is a feature-rich program and has many options to gather timing and per-thread information about the calls, and also to report the stats about the calls. we will see two common invocation lines. Here's one to collect the statistics. So you start a strace suggested in that line and let it run for some time, and then simply hit Ctrl+C. And after you hit Ctrl+C, it will bring a report like the one you see here. And like the oprofile report, we can see that the percentage time is showing us 80% of the time was consumed by a single system call, select. So if we could optimize select somehow, we will certainly improve performance of the system. On the other hand, we can see that fdatasync is only eating 0.18%. So wasting any time optimizing fdatasync calls won't give us any gain. So this is the kind of things that you can get with a quick report. That's the -C modifier, and it's good to get a quick understanding of what the system is spending on, what calls the system is spending time on. Sometimes we will find a known pattern on this. And then here's another call that it actually allows us to observe the process. You will also run this and hit Ctrl+C after it's running for a while. For example, after the problem happened, or after we think enough data has been captured, we will interrupt and go over it. It's an extensive output, and we can see it's that rather than a report, it's given a sequential series of events. So you can see exactly what happened and when. We can see the timestamp with microseconds, the function name, read, open, write. The 31 in this case, for example, is the file handle identifier. The values between quotes is whatever we sent or whatever we got as back from the kernel. And the equals 4 equals 21, that's the return values. That's the error code returned by the function. You can do man read, man open, man write on your Linux command line, and it will bring out, and it will tell you about the parameters for each syscall and the return values. So actually, man pages are the most useful when working with strace. Be sure to read them. And I think, yes, here we have a nice trick which shows a nice use. When you see weird behavior, you change a myCNF, restart the MySQL, and the weird behavior is still there, and you can't actually explain why. It could be because there's some other myCNF being read that you're not aware is there. So a quick way to find out is if you run strace as suggested here, you will quickly get this output that will show you all the myCNF files the MySQL client tried to open on its way to execution. So you can do this sort of tricks. You could also see how many network connection or sockets or memory allocations or whatever goes through a system call, which is whatever happens on the system, should go through here. And with the timing information here, we could also tell, okay, there's a lot of latency between the read on the line number 6 and the next read on line number 7, the select database. That there are like 3.5 seconds in between those calls, which means either there was it was waiting for the user to input something, or it was waiting for network or some other resource. That's a very, very useful way to diagnose the system. So we are running out of time. I'm just going to show you how perf looks. Perf, you run it like this, perf top-p, and the PID of the process you want to investigate. And the output will look a bit like this. You can see it's quite similar to the oprofile, but again, perf is less intrusive and should be easier to run on a wider array of setups, especially because oprofile has issues with virtual machines where perf should work perfectly because it's a clean API and not a kernel hack like oprofile was. So if you need to choose, try to choose perf to start, and if that doesn't get it, go with oprofile. So I'm all done, and let's go over the questions. If Matt and Elisa want to help me on that.
Sure. Thanks, Marcus. I've got a few questions, and just want to remind everyone, if you have any questions, please type them in and ask them, and we'll see if we can get to them during this webinar. If we can't, then we will follow up with a blog post on the MySQL Performance blog with our response. So, Marcus, what applications do you recommend to track these metrics and establish baselines?
Well, Cacti is by far our favorite. Cacti, we have what's called Percona monitoring plugins, which work for Cacti, Nagios, and Savix. And those will give you decent graphs. You can get 10 seconds granularity, which is decent enough. And it has saved our lives many times. So that's the best one I could recommend.
Okay, thank you.
Now we also have Percona Cloud tools, but those don't show system. They only show MySQL metrics.
Okay. Are there any risks in running these tools in terms of impacting the resources they're intended to monitor?
Okay. oprofile will impact. Top won't impact. vmstat won't impact. iostat or PT disk stats won't cause any impact either. And strace and GDB, as we warned, those won't impact on performance, but they can crash the service. So while they won't have an impact on the performance itself, they could lead to an undesirable state.
Okay. Would you ever use MySQL build and debug options instead of these tools, and when?
So if you mean building a MySQL-debug binary, yes, we have used that when tracing complicated bugs that we couldn't see the path that led down to the bug. So sometimes you need to capture all the iterations. oprofile, for example, will show you only one bug trace, but it won't show you through time how many all the paths that a certain session has followed. It will only show you the last one. So when you need to see all the bug traces that have been executed one after the other, you should use a MySQL-debug binary.
Okay. Got a attendee that said they've encountered a lot of errors, like got timeout reading communication packets. The error seems impossible to trace. Do we have any recommendations on how to solve such an issue using these tools?
Okay, so there's one we haven't got to, but I'll make sure to post on the blog post, to post a good sample. Basically, I will investigate. There are a few stock answers which are max allowed packet, the clients are not being disconnected properly, so it could be simply a timeout. Well, it could be communication errors on the network, so TCP dump is very important for this, as well as netstat-s. That, let me go through the slides very quickly. So netstat will show you all sorts of statistics, and very extended statistics. And it's a complex output to digest, but if you can send us that information, and we can check that. Usually our forums are open, and the support engineers do work on the forums often, so you can feel free to post samples there of your data, and we'll be glad to check there.
Great. If anyone has any other questions, please type them in. I think that's all the time we have to address questions here on the webinar, and I'll hand off to Elisa to wrap it up. Thanks, Marcos.
Okay, Marcos and Matt, thank you very much for today's webinar. Everyone, I hope that you did enjoy today's show, and I would like to invite you to attend the next webinar, which will be April 30th, and it's about, it's by Peter Zaitsev, and it's called MySQL Indexing Best Practices for MySQL 5.6. And there is another performance optimization webinar also by Peter Zaitsev on May 14th. So I do highly encourage you to attend or at least sign up, and we'll make sure that we send you a recording. Speaking of which, everyone will get a recording, a link to the recording of this presentation as well as the slides within the next 24 hours. So with that said, thank you everyone for attending. Again, Marcos, Matt, thank you for your time today, and I hope everybody has a wonderful rest of their day. Take care, everyone.
Thank you, Lisa. Thank you, Matt. Thank you, everyone. Have a good one.